Made it. Good call. As I was preparing for today, I think I mentioned in class that I was going to have to lecture over the last little bit of resonance for today's lab. And I decided that I would also lecture today on a little bit of music theory, how we get the scale and what things like a fifth mean and so on, and replace the scientific method part with that lecture so you don't have additional time involved. So you don't have to do a scientific method part for today's lab.
So we just have to like write down the procedure and stuff and fill that out?
And do the experiment.
And do the experiment?
Yeah.
But we don't have to like write up a conclusion or anything else?
Well, no, you always have results and conclusion.
But we don't have to do any of the
But
observations of any of that.
you don't, right, you don't have the observation, the hypothesis, and the test.
Okay. Apparatus and all that?
But yeah, you have that. You have everything else.
And the equations.
I'm glad you're excited about that. Okay, so let's get into this. We talked about beats. I have the example of beats with my two tuning forks. But I've made a change between the tuning forks. I took off this putty. I sure hope I can get them back on. Taking off that putty changes fundamentally the tuning fork. It changes the mass here. And these here are acting like simple harmonic oscillators with masses on a spring. This isn't a normal spring, but it's still steel that has a Hooke's law relationship between how much we bend it in and out and the force. So I'm going to play these both at the same time now. Do we have beats?
No.
What's different? With the answer is yes.
Do it again?
Do it again.
Still going. It's a much longer time between the beats, a much longer period. If it's a longer period, what does that mean about the frequency?
It's smaller.
It's a lower frequency.
Oh.
And so that means that the two frequencies themselves, as Max said, are closer together. Because the difference in frequency is that beat frequency. So now they're almost the same frequency. Why did I do this? Because David wanted me to.
I showed you a video.
And then he said, I said, I can totally do this. And he said, well, that would be really cool. We should do it.
Okay, fine.
So I'm going to move this back so it is just touching that ping pong ball. Now I'm only going to hit this one and not touch that one. See the ping pong ball? Why is it doing that? Because this tuning fork is vibrating. Why is that tuning fork vibrating? Okay, they have almost exactly the same frequency. And this here is called a resonating chamber. It's a region where sound waves can bounce back and forth. And if you have the right resonance conditions, which is what we were starting on last class period, we're going to finish on today, then you will have, like pushing somebody to swing at the same frequency that they're swinging. Each time you push, you're adding energy so that you have higher and higher amplitude, which means louder and louder sound, comes in here, resonates in here, and transfers to this because it's now driving the tuning fork at the same frequency. The tuning fork will vibrate. So it's a pretty cool example showing how the energy in the sound waves transfers. Waves fundamentally are carrying energy. And you can see that result of the energy by the swing of the ball. Let me take this down now so it's not in the way of everything. Also going to grab this again. Okay, we've already talked all about this. I just wanted to show this again. Beats in space is a different thing than the beats in time. What you were listening to is beats in time. From your location, you heard it get loud, and soft. But if I have two speakers that are putting out the same frequency, based on the distance from one speaker to me and the other speaker to me, there will be some locations where the waves come in and they're both down, both up. What kind of interference do you have if they're in phase with each other. In this case, it's constructive. I know you were thinking the right thing. You have constructive interference. You have places where it's louder because the path length from one speaker to that location and from the other speaker to that location, they're either the same path length or they're different by one wavelength so that the waves are in phase. But then there's other locations where the path lengths differ by half a wavelength. In that case, when one's at max and the other's at min, and then what kind of interference do you have when they meet? Destructive. And so those locations, you'll have nothing. When I was in graduate school, okay, you know I was a nerd, obviously. I was a nerd from Southern California, so I loved to play beach volleyball. And we would go to what we called the dunes, which was on the Snake River, to play volleyball. And then I would stop in, because I was a nerd, at the power plant they had there. And you could just, back then, you certainly can't now, terrorism threats and whatnot, but you could just walk down there among the turbines. And I loved it because you're in there and it makes such a horrendous racket because you have all these turbines all rotating at exactly the same frequency, making crazy noise. But as you walk around, you find places where it's quiet because you are in a place where you have destructive interference. And other places where it's super loud. That's lower Grand Jam for anyone who cares. Yes?
Is that like what they use? Do you remember when they came out with cars that said you wouldn't hear anything inside? They were balancing out the noise.
With cars, I think they're just using insulation. But noise canceling headphones, that's what they're doing, yes. They are basically, you have a microphone, you invert the phase, and you play sound with inverted phase so that it adds up to 0. So that's what active noise canceling is doing. Some will say noise canceling, and that's passive. Yeah, then they're just using insulation. Sound insulation in this case. So that's another cool feature, something that we are going to study next semester with light much more carefully geometrically. Resonance, the topic du jour. We're going to study resonance in tubes. Now, tubes come in two varieties. You can have a tube like this that is open on both ends, and we call that an open tube. Or you can have a tube like this, almost got it, a tube like this that's open at one end, closed at the other. We call that a closed tube. Smarter. We don't have tubes that are closed at both ends for musical instruments typically because we want the sound to resonate inside the tube and then come out. Now a drum has drum heads on both sides, but those drum heads are not fixed. So it's not really a closed tube, it's actually more like an open tube because both sides can vibrate. So the difference between an open end and a closed end, these molecules cannot move. They hit the end, they have to bounce back. They can't go into it. And so you have a restriction on the motion of the molecules at a closed end. The pressure could be anything, just like a wall. I can press as hard as I want on the wall. At an open end, the molecules can move freely in and out, but the pressure at the open end, it's open to the atmosphere, so it's going to be atmospheric pressure. So the pressure is fixed. So when we talk about sound waves, we either talk about pressure or displacement. Displacement is how much the molecules are removed from their equilibrium position, and pressure, of course, you know what pressure is. So on a closed tube, on the closed end, the displacement is at a node because they can't move into the end. Whereas at the other side, the displacement can be anywhere, so it's a displacement antinode. So what's the shortest distance for a standing wave between a node and an antinode? This goes back to what we did yesterday, except we were on a string. But now we're going from a node to an antinode. What's the shortest distance you can have in terms of wavelengths, as illustrated in the picture? 1/4 wavelength. So you can have it resonate with length equals wavelength over 4. Or if I'm going to go from a node to an antinode, where's the next antinode in this picture? I'm just going to go across, and you tell me to stop when I get there, okay? So I'm going across here.
There.
That's a node. That's not an antinode. I need to go to an antinode.
Then it's halfway. Oh, okay.
Okay, that's an antinode. How many wavelengths is it from here to here?
3/4.
3/4. So I could also have length equals 3 lambda over 4. And if I continued on, how far would I go to the next antinode?
5 lambda.
5/4 wavelengths. So we, just like when we did the wave on a string, we have L sub n is equal to n lambda over 4 with the restriction that n is an odd number. So this is playing odd harmonics, not all of them. Well, I jumped ahead when I said odd. But it's an odd function because it's only odd integers for n. And it can be 1, 3, 5, etc. Now we've already learned the relationship between frequency and wavelength. And so if I solve this for wavelength, I have wavelength is equal to 4. Yeah, length. Yeah, that's right. Stop that.
So when we're talking about the lambda over 4, is that specific to resonance in a closed tube?
It's a closed tube if you have these numbers here.
Because then the other one we have is like, what is it, lambda over 2? For like the string.
For the string, we had an equation that was very similar to this. Here I've just shown what the equation is for the frequencies that will resonate on a closed tube. And this has, just substituting into that equation what wavelength is, the frequencies that will resonate are n times v over 4L, where n is an odd number. For a string, it was n times v over 2L, where n is any integer.
Okay.
So odd versus any integer, and 2 versus 4. So that's something interesting. An octave is doubling the frequency. A closed tube cannot play an octave because you can't go to 2 times the fundamental. You can only go to 3 times or 5 times. So you have different wavelengths that will resonate, or different frequencies that will resonate. Here's going to the next one that we already did. Here's showing a whole bunch of pictures so you can see. It's probably overkill, right? Open tube. This was a closed tube. It was closed at one end, open at the other. Open tube is open at both ends. Well, notice now, how many wavelengths is this? It's a half wavelength. 1/2, 1, 1.5, 2. That's exactly the same relationship we had. The lengths that would resonate are equal to n times L over, or lambda, excuse me. Lambda over 2, right? That's exactly what we had for a wave on a string. And so it turns out you have exactly the same frequency equation for waves that resonate on an open tube as you have for waves that resonate on a string. Because they both have, well, in this case, it was antinode to antinode. If we'd done it pressure, it would have been pressure node to pressure node. Whereas on the string, it was displacement node to displacement node. So you have that equation again. That's the equation we had yesterday for the frequencies that will resonate in an open tube. So in things like a pipe organ, you'll have some tubes that are open and some that are closed because they're different. They're going to make different timbres. I threw in a couple problems here. This first one should be very straightforward. Remember, there is a homework assignment due tomorrow. That is the last homework assignment. It is, yes.
So what about like the other homework assignments that are like on Moodle?
Tomorrow's is the last.
Okay. And then same thing with Pruzol?
Pruzol, I think you're done with Pruzol actually now that I think about it, aren't you?
There's like another one that's due Friday or something.
It is, okay.
You take it out though.
The last one should be from chapter 17, which all the 17 we're going to get is going to be from yesterday and today. So I'm not going to change up the Pruzol. I think I had that squared away, but yeah, we're getting done. Anyway, let's do this problem. Suppose an earthquake shakes you with a frequency of 8.5 hertz as it passes and continues on to another city 76.5 kilometers away and reaches it 15 seconds after it passes you. The question is simple. What is the wavelength of the earthquake in meters?
You said it shakes you?
Yeah, it shakes you. Yeah. Okay, let's talk about earthquakes just real briefly. Earthquake waves. We have bulk waves and we have surface waves. We learned about two fundamental types of wave. Do you remember the two fundamental types of waves? Transverse and longitudinal. Going through the bulk of the earth, you can have a transverse wave or a longitudinal wave. We call those waves S waves and P waves. P stands for either pressure or primary. In either case, it's a longitudinal wave. Missed a syllable. Longitudinal wave, and it's faster. It's called the primary wave because it's the first one to reach you. And so let us suppose that the focus of the earthquake is straight below me. So I'm standing on the epicenter. The epicenter, just some words so you don't sound ignorant with people. The epicenter of an earthquake is the point on the surface of the earth directly above the focus. The focus is where it occurs. It's also called the hypocenter. And then the epicenter is point on the surface of the earth above. So if you're at the epicenter, when that P wave hits you, what direction are you going to move? Up, because it was going up, and if it's a longitudinal wave, the motion of the particles is the same. So you're going to be going up and down when that P wave hits you. That's the primary wave or pressure wave. It's the first one to get to you. Then we have the second one to get to you, which is called the S wave, which stands for shear or secondary. It's a transverse wave. So when that transverse wave hits you, if you are standing on the epicenter, what are you going to do when the transverse wave gets to you?
Transverse, what's happening?
It's going up for a transverse wave. The displacement is perpendicular to the velocity. So you're going to go side to side or forward, backward, or, it's going to be a side-to-side motion when that one hits you if you're on the epicenter. So if you're on the epicenter, first you go up and down, then you go side to side. And they come at different times because of the different speeds. Now, if you're not at the epicenter, here's the Earth, here's the focus, and let's say that you are here, you're going to have, a wave that comes like this would make you go like that or like that. So you would have some different types of motion. Then you have waves that once they've hit the surface, they travel outward. And that's where things get interesting. Because those waves that travel outward are a combination of longitudinal and transverse. And so we have waves that we call Rayleigh waves that are kind of like rollers. And we have love waves, which I think are There's different kinds of surface waves with earthquakes. There's a lot that goes into earthquakes. And studying earthquakes is really important for our knowledge of the interior of the earth. We have never been able to get past the crust of the earth. The earth has a crust, which depending on where you are is ranging from about 7 kilometers to 30 kilometers thick. Continental masses are less massive, and so they float higher. And so we are on a thicker, less massive piece of crust, whereas oceanic is thinner and more dense. We've never been able to drill through that, so we don't know anything about what's below there from direct observation. How do we know about what's below there? Mostly from seismic waves. Earthquake waves, their speed depends on the composition of the material, and the pressure of the material, and the temperature of the material. And so by tracking earthquake waves, you have an earthquake here, and then you have observing centers all over the earth. They can track how long it took for each type of wave to get to each location, and then calculate where it traveled and how the speeds varied. So it's almost like they're doing a CT scan of the earth every time there's an earthquake, or every time some rogue nation detonates a nuclear bomb. You know, North Korea was doing that on the weekly a few years back. And so anytime that happens, all the scientists are gathering data. That's how we know about what's going on inside the earth. Back to the problem. It doesn't say which type of wave it is. Obviously, the first one to get there would be a pressure wave if it was going through the bulk. How do I find the wavelength? Wavelength is equal to velocity over the frequency. So, does this tell me the velocity?
No.
No. What do I have to do?
Convert kilometers to meters and divide that by 15.
Okay, velocity is equal to distance over time. So that's going to be 7,600 meters. There, I converted it from kilometers to meters, divided by the time of 15 seconds. And
that's 5,100.
Then put that in here. Really, 5,100?
Yeah.
Okay. Over the frequency of 8.5 hertz.
And you get 600 meters.
600 meters. That's a long wavelength, isn't it? I don't have anything in today's lecture about tsunamis, but I should talk about tsunamis. First, the funny story. In America, what do we usually call tsunamis?
Big wave.
We call them tidal waves. But you can call it big wave too. I'm good with that. But it turns out that tidal wave is not a preferred scientific name. So let's talk about what these words mean. What does tidal wave mean? That's why it's frowned upon scientifically. People think it has to do with tides, like high tide, low tide. I believe it actually comes from tidal areas. You know, places where you have tide pools.
Yeah.
I think that's where it actually comes from. And if people connected that with the name, then it wouldn't be a problem.
Well, I mean, I guess that makes sense because like usually, like it floods first and then the wave comes. That makes sense.
Yeah. The name in Japanese is tsunami, which literally translates into harbor wave. It's a wave that you see in the harbor. What causes a tsunami? What do you know that causes a tsunami?
Underwater earthquakes.
Okay, underwater earthquakes. You take, wow. It was around 2004, I think, there was this really big earthquake in, I don't know how to pronounce it, ACEH.
ACE.
Yeah. And I believe you had the ocean floor shifted by something, I don't know if it was 2 meters or 10 meters, but it was a big shift. And so if you lift all that water, what's the water going to do? It's going to run off to the sides. And so you have a bunch of water running off to the sides. And that creates a shock wave that travels through the water. Now, deep water has, deep water, believe it or not, in this case, the ocean is considered shallow water. Shallow water waves have a speed that depends on the depth of the water. And so the deeper the water, the faster they travel. And so these waves go ripping across the ocean. And you have all of the water going like this behind the wave. And then when they get to shallow water, the speed of the wave drops. And if the speed of the wave drops, the energy can't go anywhere. And so instead of all of the water moving, faster, it builds up higher. And so you build up a big wave when it gets to shallow water. Hence the harbor wave. It means that you don't see the wave until it gets to the harbor. Now, if you fly over with an airplane, I told you can see a tidal wave as it's going through the water, or a tsunami as it's going through the water, tsunami. Because all of your little waves are closer together after the tsunami has passed. So it kind of looks like there's a shadow there because you have light being reflected less back toward you. So you can kind of see it. But tsunamis may be a couple inches tall as they go through the ocean. But when you get to the harbor, then they become feet tall. And it's not just a normal, 10-foot tall wave, because all of the water behind it keeps going with it. A normal wave, the water behind it goes back. Here it just all comes. So the wave comes and hits, and then the water just keeps on coming. So that's the basics of what's going on with tsunami. And then, of course, you have the forward surge, then you have the backward surge. So water level goes up, and water level goes down. Actually, usually I think it goes down first, then it goes up. It's, I'm sure, scary. I've never seen one. All right, so moving on. Question, Andy.
Google says the shift was 9 meters west-southwest.
9 meters southwest?
The thing shifted 9 meters across.
9 meters is huge,
Yes.
right? Southwest is not up or down. There was also a vertical component, so maybe it was 2 meters of vertical component. Okay, talking about the loudness of sound, or the volume, as we talked about in class yesterday. It has to do with the amplitude. Here, I'm focusing just on the intensity of the sound. Intensity is power per unit area. Power is energy per time, right? So this is equal to energy per time multiplied by area. If you have a sound wave, such as the sound wave coming out of my mouth, there's a certain amount of energy per second coming out of my mouth. And right here, it's all concentrated in a very small area. So the intensity is pretty large right next to my mouth. Hence, if I put my mouth right next to your ears, and I speak the same level that I'm speaking now, you would hit me, right? That's way too loud. But as it goes away, the area becomes much larger. So if you go 1 centimeter away from my mouth compared to 1 meter away from my mouth, the area of a sphere, because it's spreading out as a sphere, is proportional to radius squared. So if it's 100 times farther away, your area is 100 squared, or 10,000 times bigger, which means the intensity is 10,000 times smaller. So the intensity drops off as 1 over radius squared, because area, you guys probably don't know the equation for the area of a circle, but it's 4 pi r squared. And so the intensity is the energy per time, or power, divided by 4 pi r squared. Now, when we talk about how loud something is, we compare it to a reference level. So this equation here, beta, stands for the intensity level. Not the intensity, but the intensity level in decibels. Deci is a prefix. What does the prefix deci mean? It means 10, 1/10. That's why there's a 10 out front. Because we're taking the bells, the log of I over I0 would be the number of bells. And then we're multiplying by 10, so we get into decibels. And so it's the intensity divided by reference intensity. That reference intensity, 10 to the minus 12 watts per meter squared, is the threshold for hearing in some theory. Everybody's threshold for hearing is going to vary a little, and it also depends on frequency. In fact, people with good hearing can hear below 10 to the minus 12 watts per meter squared in certain ranges where you have best hearing, which is around 1,000 to 5,000 hertz. But this is how we calculate decibels. So as I'm up here speaking, do you have any idea how loud the sound is you're hearing in decibels? The intensity level? It's somewhere in the ballpark of 70 to 80 decibels. 60 would be a nice quiet conversation. 50 would be, whispering. 90 would be annoyingly loud. So it's somewhere in that ballpark. Now, if you calculate, let's say that beta is 80 decibels. This is log base 10 if it doesn't say the base. We can calculate what the intensity of the sound is at your location where you're hearing 10 decibels. So if I take this equation, the first thing I would do is divide both sides by 10 dB. Divide both sides by 10 dB, so I have 8 equals log base 10. I started to write 10 if you didn't notice. Log base 10 of I over 10 to the minus 12 watts per meter squared. The next step, what does it mean if I have a log base 10? It's kind of a question. What power would I have to raise 10 to get this value? And so I can take the inverse of log base 10 by raising 10 to the power. So what I get is 10 to the 8th is equal to I divided by 10 to the minus 12 watts per meter squared. Now it's simple. Multiply both sides by 10 to the minus 12. 10 to the 8 times 10 to the minus 12. You add those exponents, you get 10 to the minus 4. And so the intensity would be 10 to the minus 4 watts per meter squared. In your homework, that's actually one of the numbers in your homework, 10 to the minus 4. Talking about, no, it's not 10 to the minus 4, it's 10 to the plus 4. Talking about breaking up gallstones, I think it is. So that's how the decibel system works. So let's take another comparison. So Anna and Aaliyah are approximately 2 meters away from me. Okay, I'm going to step a little closer. There, now they're pretty much 2 meters away from me. David's about 4 meters away from me. How does the intensity level that Anna and Aaliyah hear compare to the intensity level that David hears?
Is it 10 decibels for David?
Well, let's start with the simple. David's twice as far away, right? What does that do to the intensity?
Divided by 2.
Not divided by 2 because it's divided by radius squared. So if we double the radius, we have to divide by 2 squared. So it's 1/4 the intensity that David's hearing. And so then the question is, what difference in decibels does it make if I have 1/4? Well, I can just take the relationship. So beta for Aaliyah is equal to 10 log of intensity Aaliyah over I0, right? And beta for David is equal to 10 log, and his intensity is 1/4, so there I've written out what the intensity levels are for each of them. But fun rules for logarithms. If I have log of parentheses a times b, what can I do?
What is the exponent? No. Oh, a divided by minus.
I can separate them as two different things. Log of parentheses a times b is equal to log of a plus log of b. And so this would be 10 log of 1/4 plus 10 log of I aliyah over I0. Well, this here is the intensity level that aliyah hears. So what David hears is the intensity level of aliyah plus, and you might be really concerned because of that plus sign, 10 log of 1/4. But log of 1/4 is negative. Log of 1/4 is equal to minus log of 4. And so if you put in the log of 4, you get, well, what do you get? An error.
I just got a quick question about the law.
something.
Okay, so this would be, multiply that by 10, we have minus 6.02 plus the intensity of aliyah.
Wait, log of 1/4?
Well, log of 4 is 6.0 or 0.602 multiplied by 10, you get 6.02 minus because it's 1/4, not 4.
Gotcha.
Question, Randy.
I was just confused on. Sorry.
We're good?
Yeah.
So notice there's some cool math you do with logarithms here. Finally, rules of thumb. If something is twice the intensity, then you would have, using the same rule, the intensity level increases by 10 log of 2. 10 log of 2 is 3.0 something. And so if your intensity level goes up by 3 decibels, it's twice the intensity. And of course, if it goes up by 6 decibels, then it's 4 times the intensity. Basic rule of thumb goes on. If it goes up by 10 decibels, then it sounds about twice as loud. Now, 10 decibels, that's a whole lot more than doubling the intensity. So our hearing is not linear. As the intensity goes up, it doesn't sound that much louder, which is why I can speak with one volume level, and it's reasonable for everyone. It's not super loud for the people in the front row, and it's not super faint for the people in the back, because we have a broad range that sounds, not that different. Okay. Oh, no, this is the problem I was talking about. It's not in your homework at all. It's one that I prepared for the lecture. Ultrasound waves at intensities above 10 to the 4th watts per meter squared can do serious damage to living tissues. Good to know. In fact, when we talk about sounds, I said the threshold of hearing, 10 to the minus 12 watts per meter squared. The threshold of pain, the standard we use, is 1 watt per meter squared. That's a range of 1 trillion in intensities between the faintest we can hear and where it starts to cause pain. Starts to cause pain, well, then you start to cause damage to your hearing instruments. Prolonged time at high levels causes more damage. This is 10,000 times higher than that threshold for pain. But then it says that corresponds to 160 decibels. Why 160 decibels? Well, just think about this real quick. Beta is equal to 10 log base 10 of my intensity, 10 to the 4th watts per meter squared, over my threshold intensity of 10 to the minus 12 watts per meter squared. What's 10 to the 4th divided by 10 to the minus 12?
It's going to be 10 to the 16.
Right. The watts per meter squared cancel out. But of course, since log base 10 means what power would I have to raise 10 to get the thing in parentheses, clearly you'd have to raise 10 to 16 to get 10 to the 16.
So then the level of decibels for intensity of 10 to 5 would be 170 decibels.
That's right. And so that's what this asked, yeah. You answered it too quickly. Took away my thunder of, now let's do the next one. Good job. Everybody see how he did that? Some said yes, some said no. He just said, okay, now we have a new beta prime is equal to 10 log base 10 of 10 to the 5th watts per meter squared over 10 to the minus 12 watts per meter squared. And he said, well, 10 to the 5th divided by 10 to the minus 12 is 10 to the 17th. Log base 10 of 10 to the 17th is 17 multiplied by 10 equals 170 decibels.
So is 10 to the negative 12 watts per meter squared always going to be on the bottom?
No. I would like it to be, but it's not. If you were to go to my sound system at home, I usually watch TV with it set at minus 25 decibels. Minus 25 decibels means that my intensity is lower than I0. Clearly, it can't be lower than the threshold for hearing. In this case, the reference is the recording level, the level the sound was recorded at. So I'm listening 25 decibels below the level it was recorded at. And of course, how loud it really is depends on your speakers and a bunch of other things. My speakers are not high tech. They'll think I'm booming sound. All right. Now the music. The music, and then we do our experiment. So, anybody ever thought about why certain nodes are concordant and concordant and others are dissonant?
Yes.
Some have, some haven't, okay? Have you come to any conclusions or read up on it, or just thought about it?
I've thought about it and I've pondered it, but I haven't actually looked anything up.
Okay.
So it assumes like the way that the waves hit each other has an effect.
It's something that obviously musicians and scientists such as Pythagorean and Eratosthenes have looked into. And so when we're listening to musical notes, we're mixing frequencies. And Pythagoras is the one who gets the credit for doing the original work on this, and I thought that it was going to be in that one, harmonic or frequency analysis. Let's just get to Pythagoras. Oh, I forgot I have like 4 slides of different instruments. Remember from class yesterday, I showed how you have like different sounds. When Max said ah, we had a completely different set than when we said E of frequencies. So different instruments are going to have different combinations of harmonics. So I believe this is from a guitar. Does it say there? I think it's what it's, the frequencies you get when you pluck a guitar string. And then a different instrument, it's plucked different places. This is plucking the guitar string near the bridge, the other one is plucking near the center. By plucking a different place, you have a different distribution of frequencies, hence a different sound or different timbre, different quality of the sound. Okay, go quicker. The Pythagorean tuning, which is where I wanted to go next. Pythagoras, by experimentation, noticed that if he had identical strings and put the same tension on the strings, that 2 notes on plucked strings would sound good if the lengths were small integer ratios of each other. So for instance, if the ratio of lengths was 3 to 2, it sounds really, really good. In fact, that's the best you can get is a 3 to 2 relationship. We call that, we'll see, it's called a fifth. And so Pythagoras actually came up with a scale, and like I said, some people credit it to Eratosthenes, some to Pythagoras, but came with a scale that's based on the 3 to 2 ratio. Everything in the Pythagorean tuning is a 3 to 2 ratio from another note or an octave. Octaves is doubling the frequency. So 1 to 1 and 3 to 2 are the 2 ratios, 2 to 1 and 3 to 2 are the 2 ratios used in a Pythagorean scale. And a Pythagorean scale is going to sound beautiful, but you can only use certain notes. So that can only use certain notes is a little bit troubling. You have 8 notes that make up an octave. Octave, obviously the oct is 8, but octave is the term we use for doubling the frequency. So there's 8 notes and doubling the frequency. If you're counting the notes, it's important to realize that in music we count the starting and ending notes. So an octave, if you go from C to C, the first C and the last C both count for the 8. So the Pythagorean tuning is what dominated music for a long time. But the problem is you can't change keys. If you're going to play a song in the key of, C major is that a key? I don't know. It's been a while. All the instruments have to be tuned just so, and you can play in C major and it sounds beautiful. But you can't modulate. You have to stay in that same key. So we have other types of tuning that we use. Now, the first thing I'm going to go through here is talking about intervals. And so an octave is going, doubling the frequency, and it's 8 notes. 1, 2, 3, 4, 5, 6, 7, 8. And you probably all learned from The Sound of Music, do, a do, a female, do, re, a double golden sun. Or from classroom music, at least when I was a kid, do, re. I don't remember the rest, but we had to use hand signs for all of those. A fifth means a 3-to-2 ratio. But that 3-to-2 ratio, 1, 2, 3, 4, 5, hopefully I counted right, yeah, C to G is 5 notes inclusive. And so that fifth is a 3-to-2 ratio. And like I said, fifths are the best consonant sound you can get. They sound the most beautiful together. But you can go a fourth. A fourth is a 4-to-3 ratio, and it's 4 notes. So the fourth is going from, for instance, C to F. And of course, the reason I have the C scale is because there's no accidentals in the C scale. You just count the white keys. So a 4-to-3 ratio is a fourth. What do you suppose the next ratio is going to be?
Third, fourth.
Okay, it's going to be a third, which means it's going to be going from C to E.
2 to 1 or something.
Not 2 to 1, that's an octave.
Then it's a 1 to 2.
So octave is 2 to 1, fifth is 3 to 2, fourth is 4 to 3. What's the third going to be?
3 to 5 to 4.
5 to 4. The fifth is a 5 to 4, or third, excuse me, is a 5 to 4. And notice this time I went ahead and put in the major third. What's the difference in a major third and a minor third? I had to look it up. Yep, minor's a half step down. So you can see that there is a physics reason for the notes we have. Except for what we have here, what we've defined here is called a just tuning scheme. The just tuning scheme is setting your frequencies by the small integer ratios, not just 3 to 2 and 2 to 1. So this is called just tuning. You know what we use in our concert bands, in our orchestras?
Not this.
Not this. We don't use the Pythagorean tuning. We don't use the just tuning. We use chromatic tuning. So, I thought that was my next one. The just tuning is what we just, I just talked about just tuning. We don't need to talk about it again. Oh, did you notice the last one there? Very important to me. A cappella groups, such as barbershop quartets, usually use just tuning rather than the chromatic tuning that you use in an orchestra or band, because you know what? Your voice is completely flexible. If you are a company, you can choose whatever scale you want, and the just scale is going to produce better harmonies. I assume that's why I like quartet music so much, because the harmonies are just so tight. Summarizing, this is just showing a summary of what the third, fourth, fifth, and octave mean. So we've already covered that. Here is a comparison of the different scales. The Pythagorean, remember the Pythagorean scale comes from taking 3 to 2 ratios and 2 to 1 ratios to come up with your complete set of 12 tones.
Wait, it's not 4 to 3. It's 3 to 2 and...
The Pythagorean is only 3 to 2 and 2 to 1. The just scale is using 4 to 3 and 5 to 4 as well. So the just scale, that's the one that we actually are talking about most, like for barbershop quartet and stuff, because it's using those ratios that are going to sound good together. The reason for the Pythagorean one is because the 3 to 2 is the best you can get for sounds, meshing. But for making a chord with more than 2 sounds, the just scale is going to give you the best mix. And then we have, mean tone and Werkmeister we'll skip over. This is what we use in bands and orchestras, the chromatic scale. The chromatic scale comes from looking at these numbers here and recognize, okay, we can make a total of 12 notes here if we do the scale out. And so let's just take our bass note and make each note above it that bass frequency times 2 raised to the n over 12. So this one here is 261.63 times 2 to the 112. This is 261.63 times 2 to the 2 twelfths, 2 to 3 twelfths, 4 twelfths, etc. And so you get up to this one, it's, of course, times 2 to the 12 twelfths, which means times 2. This gives you the same ratio between each half step all the way through. Now, if you look at the frequencies and compare, all of these have the same low frequency. If we look at the fifth, that would be here, 392.44, 392.00. They're very close, but not exactly the same. And so the notes aren't going to be quite as nice sounding together. But the beauty of this chromatic scale or this equal tempered scale is that you can play whatever key you want. You can modulate at will, and you don't have to retune your instruments. Okay, we'll review starting mañana. So let's get to the lab. And, I don't know if I have the lab on here or not. I didn't go check. I thought I put them all in at one point, so let's see if I did. Yes, I do. Good. I thought I put it in. So what we're going to be doing is looking at resonance in closed tubes. If you want to see some cool stuff, that YouTube video shows a plate and they change the frequency and they put sand on it, and you can see where the plate doesn't move, which is where you have, what do you call it if you set up a standing wave that's not moving?
Resonance.
Nodes. So you can see where the nodes are on the plate as a function of frequency. The plate is square, and so that sets the geometry for your waves, and you can find very complex patterns of the standing waves on that plate. But we're not going to do that because I've already taken an hour of your time. What was that? Oh, you can. I gave you the URL, so you can. So we saw that the lengths that resonate for a given wavelength are n over 4 times the wavelength if it's a closed tube. What we're going to be using today is filling this tube. What kind of tube is this? Closed. With water and putting this inside. This was open, but it's going to have water on one side, so it's effectively closed on that side. So this will be a closed tube in the end. The length of the tube will be the length from water level to the top. And we're going to test, and I will, in a few minutes, actually do a demonstration of this for resonances. So our theory says that the resonance lengths are n over 4 times the wavelength. Since wavelength is speed over frequency, our tuning forks have frequency stamped on them. And so you're going to calculate what the wavelength is using that equation, and then you're going to use the stamped frequency to find the speed of sound. That's the short of it. The long of it is just a little more, because it turns out that we lie. Of course we lie. In physics, you've learned about us making approximations. And I said that at the open end of the tube, what's the pressure?
Should be 1 atmosphere.
1 atmosphere. But the simple fact is, it's not going to be 1 atmosphere immediately at the end of the tube. It's going to be a little bit outside of the tube where it reaches 1 atmosphere pressure and stays there. So it turns out that the pressure node is not at the end of the tube, but a little beyond it. So that means I have to modify my equation. The effective length is equal to the theoretical length plus an end effect which is, or excuse me, the ln is the measured length. So ln is what you're measuring. And ln is a constant that we're going to find out, and that's equal to n times v over, well, I put v over 4f. I don't even know why I did that. The important equation is 10.7. So 10.7, we solve for the length that you're measuring is equal to n times wavelength over 4 plus the end effect. So what you are going to do is first take this thing and fill it with water. We'll do our best to not make a mess. Andrew, can you go get one of those big beakers from up here near the front? One of the goals is to not get hurt, so we want to keep the floor dry as much as possible. So, yeah. So I have buckets for you to put these in. Andrew's going to bring out a beaker, and we can use the beaker to pour water in here instead of making a mess like I did. Now, when Andrew gets here, I'm going to have him help me, but we're going to grab a tuning fork. And I'm grabbing one that's stamped 1024. It also says C. 1024 means that, at least in theory, it's 1024 hertz. These are probably, people misuse them. They'll like hit them on the tabletop. That's not good, okay? Don't do that. Hit them on a rubber stopper. We only have 4 here, so we'll have to go find some more. That's what I get for loaning my stuff to biology. One year they didn't even give it back. I had to go find it. They just stored it there. Andy, come on up here to help me. So this is 1024 hertz. Go ahead and hold this. And I'll get you meter stick so we don't get that far, and then I have to walk away. So I bang this on my stopper. Down an octave below it, but getting the pitch. Put it here. Here, I got loud. So there's softer, louder, softer. So what you're going to do, find that place where it's the loudest. Now, this is a 2-person job. So Andrew is going to hold this. So he has his finger up here so he can lock down when I say there. So I'm going to slide it up and down. He lets it move freely. It says it's a little off. Although it says from A, this is supposed to be C.
It freezes a lot when
Oh,
use the tuning.
Okay, well, anyway. There. Okay, so there he has it locked in. Now, I'm the one doing this data. So he's just holding stuff. I found the height, now I'm going to measure. So I take my meter stick. Remember, don't use the end of the meter stick because it's not calibrated. So I'm going to measure from 10 centimeters, put 10 centimeters on where the water is, and then measure the height here to be, it's at 17.3 plus or minus about 0.1 because I'm reading hard. So take away 10, I have 7.31. Now we look for the next one. So he locks that one in, and we measure it. And we keep going until we have all of the frequencies that will resonate. So just going quickly. Next one, next one, next one. I skipped one. But go all the way up until you pull the bottom of the tube out of the water. Once the bottom tube is pulled out of the water, you're done. Question, Max.
With the meter stick, you measure from the water or from the top of the tube?
From the water to the top of the tube.
Wait.
From the water level here to the top of the inner tube. Yeah. Now, I want you to notice something, especially these older ones. This says 320. Hear that high ring? That's not it. That's it. So this here is resonating more than one frequency. You want to hear that fundamental. Bring it up to your ear so you get the fundamental. That's not it.
No.
That's not the low pitch.
Oh, shoot.
There it is.
There it is. So you need to be careful. Make sure it's the right frequency that's resonating. Yeah, that's why I brought it here, so I would know which one it is.
So it resonated at 3 different ones? Or
Well, it should only be one, but the problem is people do things like they bang them on a table. It damages them a little, makes them so they do things a little differently. So each student is picking a tuning fork and a different one for each person in your group. At least one group will have 3 people in it. Each person will be doing their tuning fork. So each of the 3 people will choose a different tuning fork. And you're going to then measure all of the resonant frequencies, make a graph that has N on the horizontal axis and L sub N on the vertical axis. The slope should give you, well, looking at that equation, what should the slope be? Y equals mx plus b, right?
Should be N.
No, N is your x.
It's velocity over 4.
Go to the right one.
Oh,
Wavelength over 4.
yeah.
So you find the slope, you multiply by 4, and that's your wavelength. Also, record your end effect. So you have 2 results from your data. You have the wavelength and you have the end effect. From that wavelength, you're going to calculate the speed of sound. Then come up, just put it in there. Come up here and read the temperature in Fahrenheit. Convert from Fahrenheit to Celsius. And then use either one of the 2 equations in the lab guide to calculate the speed of sound and air and find percent error difference between the speed of sound you found and the theoretical speed of sound based on temperature. Now, you should have very accurate data here. If you're not close to correct, you made a mistake. Common mistakes are not identifying the right frequency or right resonance. You know, if your ends are off, you're off. Other things that you could do would be to, well, it's possible that you can misidentify the frequency, but not that hard because it's print on here. You can measure your distances wrong. You know, some people will make the mistake of like, well, I'm going to measure from here to here, you know, from top of one tube to the top of the other, like Max was asking about. If you do that, you're obviously going to have not correct data because the water level changes every time you raise the tube so much. Okay. That's all you're doing. You don't have to do the scientific method step. So each person chooses their tuning fork. They make sure you put your partner's data in and not just your data. That you find the speed of sound, the percent error difference between speed of sound theory and practice. Any questions? Oh, yes, that's right. You had a question, and I said I got to, and then I didn't come back to you.
So I was wondering, with raising up to, after you like hear the loudest one, you still want us to measure the other ones?
Right, we want to measure all of them.
Okay.
Because it'll resonate at this length, then about approximately 3 times that, approximately 5 times, approximately 7 times, because it's doing the odd harmonics. So you want to catch all of them. So you can, obviously you don't want to cheat and say, I found the first one, I'm just going to multiply by 3, 5, 7, because that won't be right. But it should be close to that, so you can, if it's not approximately, if the next one applies not approximately 3 times the first one, you know one of the 2 is wrong. Okay, at least 2 people in a group, 1 group will have to have 3. You can all be in 1 group if you wanted, but it's just going to make life hard.
Ours is the 3 group.
Oh,
Also,
yeah?
I have something funny.
No, I have a team.
Okay.
Yes.
I need to say something really awesome.
I want to see something awesome.
Okay, look. Look at that.
Silver.
You said it.
You said it earlier.
You're giving out vessels.
What's this?
Oh, yeah. Okay. Yes. That's an L-O-G. The number bells, yes. I read that as L-A-G.
It's silver bells. Oh my god.
I'm sorry, I'm so bad.
What?
That's silver. See the periodic table. I think that this.
Oh, so that is A-G. Okay,
Yeah.
that's log there. Huh.
Okay.
I thought that was
Sorry, Wes.
can't be the same, yo. Are those the same? No, okay.
Check this out.
Okay. Put some more water in it.
Yes.
And if you want to go to another room where it's quieter, you can do that. I would definitely recommend spreading it on the board.
Because apparently we need to do that.
Okay.
What did you say? What? It's too funny. Let me just pick it up and then use it. Right? I just got my shit.
I should point out the last final grades may change just a small amount because we had a miscommunication between Andrew and I. So they weren't completely graded when I posted the grades before. What?
I literally passed the move.
They're on the table right there.
I want to hear it.
Probably.
Why don't I just Yeah, I thought the top, yeah.
Wow.